Hello and welcome to CPE 350, Chapter 6, Section 6.1c, where we're continuing with example 11 by calculating the actual temperature profile in the fin and introducing the Biot number to describe the behavior that we observe. So again, we're solving this temperature profile in a fin, and previously we had non-dimensionalized the governing differential equation and its boundary conditions. So we'll move forward from here. We recognize that the governing differential equation is the Sturm-Liouville equation, and so we can immediately write down the solution, no calculation necessary. It's a combination of Cauchy and Cinch. Our first boundary condition is the Dirichlet boundary condition, and it says that at theta equal to 1, theta equals 1 when xi equals 0. Our Cauchy term goes to unity, our Cinch term goes to 0, and we can solve for our first constant of integration a, which has a value of 1. We substitute a equal to 1 into our solution, and the coefficient of Cauchy goes to 1. Now we need to solve our second boundary. Now we need to apply our second boundary condition, but first we have to differentiate theta with respect to xi, because remember that second boundary condition is the Neumann boundary condition that describes the derivative of theta with respect to xi. So we differentiate theta. Differentiating hyperbolic Cauchy and Cinch is very similar to differentiating sine and cosine, except that it's always positive. The constants lambda come out front because they're multiplying the variable of differentiation, xi. And we can plug in for xi equal to 1 and set the value of this derivative to 0, because that is boundary condition 2. When we do that, we're able to rearrange this equation slightly and solve for b, which is just the negative of Cinch over Cauchy of lambda, and as you might expect, that's just the hyperbolic tan of lambda. So we have a value for b that we can then substitute back into the solution to our governing differential equation, and we finally have the complete solution. So we can leave this in its non-dimensional form, and that's what we'll do for now, but you could also just replace the variables theta and xi to redimensionalize it if you wanted to use it with dimensional boundary conditions. Let's have a look at this solution. This is temperature profiles of theta versus position down the length of the fin, xi, for different values of that eigenvalue, lambda. So at very small values of lambda, we've got a situation where the temperature of the fin is almost constant. It just drops off a little tiny bit as you move across the entire length of the fin to the tip. And so that means conduction is very fast. The system in this situation is convection limited. Moving to the other side of things, if you have a relatively large value of lambda, you have a situation where the temperature profile down the length of the fin is also almost isothermal, because all of the heat is lost in the first Looking at the opposite scenario, where lambda is rather large, we have a situation where convection is much, much faster, and the situation is conduction limited. And neither of these scenarios are usually really what we want in a fin. We want something in the middle, but that will depend on the cost of the material the fin is made out of, how long you can practically make the fin, how much surface area you can build into it by, say, instead of leaving it as a rectangle, maybe wrinkling it up a bit, folding it like a radiator manifold. In either instance, the fact that lambda has such a profound effect on the shape of the temperature profile means that it's important, and it led to the definition of the Biot number, which is a dimensionless ratio of convection to conduction. For the problem of the fin that we just solved, the Biot number is equal to lambda squared. The Biot number always has an h, which is the film transfer coefficient, and the k, which is thermal conductivity, but the characteristic length associated with a Biot number can change based on the geometry of the problem. In this case, L squared over h over 2, which we can obtain just by sort of rearranging those variables, is the characteristic length that describes the fin. This might sound a little bit wonky, but if we think about what h is, it's that very thin dimension of the fin. H over 2 then is basically the furthest distance that heat would have to transfer by conduction to get to a surface where it can convect into the air. So that's where h over 2 comes from as a relevant problem. The length of the fin, of course, is very important. And so if we look at that characteristic length, we see that increasing L increases the conductive resistance because there's just more metal for heat to conduct through. Conversely, increasing the height of the fin increases the resistance to convection. It's a rough way of thinking about it. And so again, we see this ratio between conduction and convection, but in this case, it's the ratio of the resistances to conduction versus the resistance to convection. A little bit confusing. If it's easier for you to think of it as the rate of convection over the rate of conduction, that's fine. In any instance, the Biot number determines the temperature profile across the width of the fin. So this is in the y direction, and at a very low value of the Biot number, we have a low resistance to conduction, and that means, well, conduction is fast. So the whole temperature across the width of the fin is relatively constant, except maybe just at the edges where you're losing heat to convection. And that's the scenario that we modeled with our problem, because going back to our shell balance, we decided that there were only temperature variations in the x direction, not in the y direction. If you had the situation where the Biot number was very high, you actually would get a temperature drop across the width of the fin because both convection and conduction would be sort of rate limiting in the problem. And in that case, we need to look a little bit harder at defining a realistic equation. The fact is, most fin scenarios, especially in air, have a low Biot number, and so the fin approximation that we've just derived is a very good assumption. All right, thank you for watching this video, and I'll see you for the last video in this chapter.